I appreciate it.
No problem.
All right, so we'll start with this guy. Back in 1960s, at the Mont Palomar Observatory, this guy was working at Caltech. To me, Caltech is like the best astronomy school in the world. Nothing better than Caltech. So this guy was working at Caltech, and he became extremely famous because he found something very unique. He found something called quasi-star object. Quasi-star object means it's kind of like a star, but it's not a star. Some sort of a thing like a star, star-like something. So now we call it a quasar. And we had no idea what these quasars are. They look like stars, and they change their light, like one day. So how could something change its light in one day? It's like one light day across. One light day is like 3 times the size of the solar system. That's pretty small. And since light travels at the speed of light, it had to be small to change its light that quickly. So we couldn't figure out what this is. For the longest time, we couldn't figure this out. And it turns out that this thing here, according to the redshift, was about 2 billion light years away. So what could possibly be billions of times more luminous than the sun, and yet so far away, and so luminous and so tiny and all that? Well, it turns out, let's see if you guys can guess. Can you guys guess what this could possibly be? This quasar, quasi-stellar object? It turned out that it is...
Supernova?
Supernova?
No. It's an
Body.
active supermassive black hole. So our supermassive black hole in the center of our galaxy, not very active. It has snacks once in a while. Now these guys are going to like all you can eat. I mean, there's so much stuff. There's so much stuff they couldn't all take it all in. So what happens is that when they can't take it all in, imagine you're pouring in water for your dog, but with a fire hose. Now, you can't get it all in, right? You just fire hose. You can get some water in, but most of it goes out, right? Same thing here. So when we look at these quasars, this is what we're looking at. It's a supermassive black hole in the center of a galaxy, and it just happens that there's a lot of gas right next to it. So that's what I'm talking about when I say all you can eat gas, right? So it's going to eat all of this gas, and the gas, as it falls in, it kind of spirals in, and as it spirals in a form of a disk, then it goes really, really fast. It gets to like the speed of light almost before it falls in. And so they crash into each other, like protons hit protons, electrons hit protons, stuff like that. And so there's a lot of gamma rays and X-rays that are emitted. Now, that's one thing. Second thing is, as they fall in, just like I told you, not all go in at the same time. It's so tiny, you get so much gas, so they can't all go in at the same time. And black holes have these jets from north and south magnetic poles. So magnetically, these gases that are not going in, they get ejected instead. So this is the stuff that came out of the dog's dish, like that, and they eject it out. So 2 things: the light of all the stuff falling in and they crashing into each other, and also the stuff that can't go in and they get ejected at almost the speed of light, and they're ejected in these beams. So let's see, like this, exactly like this. So this is the accretion disk of the gases as they fall in. Supermassive black holes over here. So there's the event horizon. And then there is the magnetic fields. The jets are just the stuff that just can't go in at the same time. It's just, you're filling your dog's dish with a fire hose again, right? So that's what this stuff is. This is the stuff that is coming out of your dog's dish. And so this is the water going into the dog's dish. So that's what they are. There's other stuff called blazars too. The blazars are when you actually happen to be at the end of this jet. So like if the Earth happens to be at the end of this jet, we'll see a blazar. So blazar is a quasar, is lined up with the Earth, so we can see the jets face on, basically, too. Double whammy. So it turns out that the most of the massive, most of the large galaxies, medium-sized large galaxies, they do have a supermassive black holes. So we have to figure out how this supermassive black holes, some kind of a seed that the galaxies grew from. I keep seeing seeds. Yesterday, I got a whole bunch of seeds from my old basils. I'm thinking seeds. Now they get bright when a whole bunch of stuff falls in at the one time. They get really bright, and then they get fainter. And that explains why, like in one day, they can get so bright and so faint because some stuff falls in and then pause. It's like in between meals. So it becomes faint in between meals, and then it starts eating bright. Lots of stuff is going up, and then it stops eating like that.
It's eating the gas?
The gas, yeah, the gas.
So what makes it decide when to it just sucks in a certain amount, stops, and then...
Oh, it wants to suck in everything. Whatever is there is going in or getting ejected. So what goes in, awesome. What doesn't go in, it gets ejected in those jets. But as they spiral inward, the gases are colliding with each other. So we see X-rays and gamma rays coming from these collisions between the matter as they fall in. Once they fall in, we can't see it. Who knows where they go afterwards? It's a black hole, right? But before they go in, we can see them colliding with each other and giving a lot of light. And then stuff that doesn't go in, they get ejected with those beams, the magnetic fields, just like this one here. So this is an active black hole. Our black hole is very silent. It's very non-active. It's very quiet. It only has snacks once in a while. Like, it has, I don't know, like a chocolate bar once every week, something like that.
Professor, I have a question about that.
Yes.
So how is like the event horizon of an inactive black hole, is that just shorter, or is that a smaller area or volume so that less is getting consumed, or what exactly is the physical
the black hole in the center of our galaxy, I'm sure at one time was very active when there was enough gas for it to eat. But now it's eating everything. It's, when it was young, maybe it ate a lot, but now it's kind of like in a, poor folks home, basically. It doesn't get much meals. It doesn't get much gas. I think it's about 5 million years, a whole bunch of gas is going to fall in. So if you come back in your next lifetime, in 5 million years, you'll see an active black hole in the center of our galaxy too.
So it's just because it ate, or it's just because it's consumed all of a good portion of the gas around it?
The stars, yeah. Once in a while, a star comes too close, it gets used up too. It gets eaten up too.
Understood.
So yeah, or when there's a collision, there's two galaxies colliding. Oh my God! Then there's going to be a whole bunch of stuff happening.
That's when we'll see an active black hole in our galaxy again. Is when we collide with Andromeda.
Yeah, right. Then there's going to be like a starburst. First, we're going to make stars all over the place, and then we're going to have gigantic amounts of gas falling into these black holes. We're going to be quasars to the rest of the universe then, right? Like this, this is the jets coming out. In fact, we can see these guys here too. And when the guys get here, there's a lot of radio waves coming from either side of the galaxy. We call them radio lobes, LOBE, radio lobes. This is the one that Martin Schmidt found. It's called 37273. This is the closest quasar to us. It's only 2 billion light years away. Pretty cool one, though. I've actually taken spectrums of this guy. There's Martin Schmidt again. So look at this one here. This looks pretty much like what you should see. This is a light of the galaxy compared to the light that is being produced by its nucleus. So from the Earth, when we look, we just see the nucleus. We don't see the galaxy, so we think we're looking at a star from 4 billion light years away. And then we send the space telescope up. Then we start seeing pictures of the rest of the galaxy. We go, what I used to think is a star, quasi-stellar object, is now just a nucleus of a galaxy far away. Just a very active galaxy. That's all. Right. There's one that I call Blazar. I'm sorry. Question again?
Nope. Yeah. Last class we were talking about how every part of space moves like away from each other at all times, right? And so galaxies move away from each other at all times. And why do they collide?
Why do they collapse?
Why do they collide if they're always moving apart from each other?
Oh, because they're too close, like me and Andromeda. By me, I mean Milky Way galaxy. Like Milky Way and Andromeda are gravitationally bound to each other. We're orbiting together, right? The center of gravity. So yeah, so if you're in a gravitational well, then you're gonna collide sooner or later, eventually. Like in
all right, cool.
clusters of galaxy, possibility is that you're gonna collide. A lot of collisions. All right, so that's the quasars and the blazars. Now I am beginning to go to the end of the everything.
Oh, quasars and blazars again. Sorry.
Blazars are, let me go back again. Blazars are quasars. The jet happens to be shining at us like this. We just happen to be at the end of the jet. So we see these bright things, we call them blazars. Because blazars are like quasars that are lined up with the Earth. The jets are lined up towards the Earth. That's all.
Okay, thank you.
You're welcome. All right, let me kill the quasars. And we're going to go directly to God. Yeehaw. All right, you guys. I'm sorry. That's what the God looks like. God looks like a dried up pea. That's God. Okay. Now don't laugh at me. I'm serious. So this is what Stephen Hawking called the P instanton. So this is P instanton. And here you have the entire universe. Look, everybody you ever known, everything, all the galaxies, the entire universe is in here. All the space, all time, everything is going to start right here. So we say this is not a point in space. See, what they're trying to do is to get away from having a singularity. They're trying to get away with having a black hole at the beginning of the universe. So they came up with this thing here. This is called P instanton, and he did all the math. And it turns out the math is pretty much correct. Now, how did we go here, right? How did we go here?
I know, be comfy.
One momento, we have somebody that forgot to quiet themselves down.
Sorry.
That's all right. Quiet yourself down now. All right, so I don't have to worry. Good. All right, sheesh. All right, so I'm going to give you guys something just for 1 second. I'm going to go into a little short 1 minute video for you. Okay, so let's see.
Suppose you drop a ball down the side of a valley. Classical wisdom tells us that when the ball rolls up the hill on the other side, it can't go any higher than the height from which you dropped it. That's conservation of energy. Even if there's a nice big long slope to roll down on the far side of the mountain, the ball just can't get there, unless you give it enough energy to get over the barrier. But in quantum mechanics, things work a little differently. You see, the quantum world is probabilistic, so if you release a particle in a valley, chances are, the next time you see it, it'll still be somewhere in that valley. But if there's a nice big slope to roll down on the far side of the mountain, well, that's a place the particle would really like to be. And it turns out, there's also a small chance that's where you'll find it. If this isn't crazy enough, it's even possible you'll find the particle in the middle of the mountain. And in real life, this means that an electron sometimes hangs around inside the nucleus of an atom.
That's right. So electrons can actually appear in the nucleus of the atom, inside the proton. Right? So now, a proton can appear right in front of my face right now, from like 1 billion years ago, and 1,000 light years away. It just pops right in front of me. Right? That's called quantum tunneling. Happens all the time. So let's say I tried to go through the wall here. All right, wall in front of me. I tried to go through the wall. Well, you know, it's crazy. You can't go through the wall. But if you go through the wall enough, like bajillion times, you could possibly go through the wall. The probability of being able to go through the wall is there. And the atoms are doing it all the time. So an electron is doing it all the time. Protons are doing it all the time. It happens. Okay, so that's a possibility, right? So somehow we got to get this universe started from nothing. So I'm going to read this to you. This is what Stephen Hawking said. He says, this P instanton that you see here It's like full of energy, right? All the energy in the universe is here. Everything is there. It's ready to make the entire universe. However, there is no space and time yet. So everything is there. Now, how much room do I need to store all that energy? Well, no room. How much time do I need to put all that energy in there? Well, no time either. See, energy doesn't have time. When a photon travels, it's timeless. Like if you ask a photon, what time is it? The answer is, what the heck is time? He doesn't know what time is. Because if you go at the speed of light, let's say Kelsey and Linda get in a spaceship and they try to go at the speed of light, and they do. Well, now they'll be young forever. They'll never age ever again. They can go see the entire universe and come back, and they're still the same age. That's what happens if you travel at the speed of light. So you don't need time and you don't need space for energy. Sheesh. So you got everything here. Now, somehow we got to convert this energy into the universe, into matter and everything else. So let's see what we can do there, right? So before the Big Bang, you can't say what the heck was there before the Big Bang. Why not? Because it's an illegal question. Since there is no time or space, you can say, well, what was there before the Big Bang? Well, there was no before the Big Bang because time starts at the Big Bang. You can say, well, who made the Big Bang or whatever? Well, you can't say that either because there's no place, there's no space, and there's no time. So everything starts here. Now, according to Stephen Hawking, the P that I just showed you, this little P here, was about 1,000,000 billion billion, right? Million billion billion times smaller than a single atom. That's pretty small, right? And it's been expanding ever since. So there's no time or space yet. Only the laws exist. And this one makes me laugh because laws, scientists talk about laws like it's nothing. Well, and then they talk about quantum physics as though quantum physics is something they invented. Like, oh, we just found quantum physics and it's awesome that we can make, your cell phone, we can make this, we can make that. Well, so Stephen Hawking can make the universe from nothing. What he needs is quantum physics. Well, he doesn't have quantum physics because there's no time and space. So who made the quantum physics? So if there is a God, he's timeless and spaceless. He doesn't need space, he doesn't need time. So what kind of God does not need space and time? Oh, your guess is as good as mine. What kind of God can have no need for space or time? Sheesh, I tell you. So now, what happened according to what we know? Something happened between 10 to the minus 35 and 10 to the minus 33 seconds. There is something called Planck time and Planck length, which means this Planck length is something that you just can't get any smaller than that. It's like, imagine your TV set is made of little tiny pixels. Now imagine the universe is made of little tiny pixels, right? So we call these Planck size. This would be the smallest thing that you could possibly ever get to. Anything smaller than the Planck length is invisible. And Planck time is how long does it take time to travel this distance, the smallest distance. I know, it gets pretty weird, but I'm going to give you exact numbers here. What happens here between 10 to the minus 35 and 10 to the minus 33 seconds. So what's 10 to the minus 33 seconds? Let's see, it'll be 33. It'd be a billionth of a billionth of a billionth of a millionth of a second. Okay? That's a very, very short period of time. But everything happens right there. This is the time we call the inflationary time. Inflationary normally means the prices are going up, right? So this is going to go up. But this inflation is like on steroids, right? Because what happens between 10 to the minus 35 seconds is, much, much faster than a blink of an eye. The universe goes from size nothing to bigger than the Milky Way. It grows exponentially. So it becomes 10 to the 50 times bigger than it was before. Right? So that's huge. So we go from nothing to the size of, let's say, the Milky Way. What it means is the speed of light was not the same at the beginning. The speed of light was many, many, many times higher than the speed of light now. I mean, it takes 1 second for light to go 6 trillion miles. Well, this thing went like a million light years in such a small fraction of a time. Well, okay, so what gave it this bang, right? Well, the bang itself happened because gravity was acting in reverse. That's what the Big Bang is about. It's about the bang is the Big Bang. So the bang is the inflation when gravity was working in reverse. Instead of attracting, gravity was repelling. This is called inflation, right? So inflation was something that this guy at MIT found back in 1981, and he was just working out some equations. He found inflation, or how inflation was working. Uh, this guy again. Can you guys hear the guy outside cutting grass again?
Yeah, he's going nuts.
Yeah. You guys, give me a second here, please. Okay. All right. Back to the universe.
I have a quick question about the
Yes, please.
inflationary period. About how long did it last?
Between 10 to the minus 35 and 10 to the minus 33. Right? So 0 time is when it begins, but there's no inflation yet. So 10 to the minus 35 to 10 to the minus 33. This is 0.0, well, 32 zeros and a 1. So 0.32 zeros and a 1. That's a fraction of a second.
So the
Right.
Big Bang was the inflationary period, and the inflationary period is gravity acting in reverse, and it happened really quickly and didn't last long.
Very good. That's right. The period of the actual bang didn't last very long. And the universe was expanding faster than the speed of light, right? All right, but we haven't really talked about the space yet. That's the key thing, is the space itself. So let's take a look at this thing. All right, so these are all the forces now. So right after the Big Bang, here we know everything down to about minus 10 to the minus 43 seconds. That's a 0.42 zeros with a 1 at the end. So that's a really, really short time. Before that, there was one force. There wasn't 4 forces like gravity and light and all that. It's only one force. It's called God force. So God force, it encompasses all forces. Now we have everything. So on the right, we have temperatures. On the left, we have time. So we're talking about like a millionth of a second here, right? So the weird thing is, actually, Abdul Salam, this guy from Pakistan, he got the Nobel Prize for this because he found out that the weak nuclear force that decays the atoms and electromagnetic force, which is light, it becomes one force if you have enough temperature. Like if you have, let's see, 10 to the 13 degrees Kelvin, right? 10 to the 13 degrees Kelvin is 10 trillion degrees Kelvin. We can approach that temperature. At that temperature, you get just one force. So these become electroweak force. So these two forces actually become one. So if you get the temperature even higher, 10 to the 15, that's at 10 to the quadrillion degrees Kelvin, then all these three forces, strong nuclear force, electromagnetic force, weak nuclear force, become one. And if you can get this kind of temperature, now gravity becomes one force and we have God force again. All right. So forces one by one split up. First one that splits up is gravity, of course, because gravity is going to work into making the universe expand. Gravity is the key, right? Except gravity at the beginning is repulsion. It's not attraction. So now you might think inflation is just theoretical. Well, Alan Guth, he predicted what we're going to see, and we saw exactly what he said we're going to see. So let's take a look to see what we have here as evidence. Now, what you're looking at here, this is kind of funky actually. This is called virtual particles. So you're looking into a pure vacuum. This is space. That's what space looks like. And yet space is full of stuff. These are called virtual particles. Particles that come to existence having enough energy. So if you have enough energy, you can bring them into existence. But like right now, between your face and the computer that you're looking at this image, there's a whole bunch of space. These virtual particles exist between you and the computer. So the space, particles exist. Look in this example, I give you electron, positron, quark, antiquark, something like that. They exist, except when they try to exist in real space, in real life, they annihilate each other. They can't exist side by side. An electron and a positron, matter and antimatter, they can't exist side by side. So, problem. But we can see how they could exist. There's two ways we can make virtual particles exist. Well, in Star Trek, they definitely know what to do, because in Star Trek, they're making meals out of nothing, right? It's like they have a little machine that you press, like, I want beef stroganoff, and then you get a beef stroganoff in 10 seconds. So they're making food out of virtual particles. Yay. So at the beginning of the universe, we have a lot of temperature, super, super hot, and we also have a lot of energy. Gamma rays, we have those ghost particles. These are all expanding with space. So these gamma rays, I told you gamma rays, remember? They have the highest amount of energy. The energy of the gamma rays, when two photons of gamma rays get really close to each other, they can bring out virtual particles. They can make them real. And so we get a real particle, electron, and a virtual particle, a positron. So we get a positron and an electron. Somebody's got their microphone on again. Can you guys please be careful today? Because I screwed up the other class's video, so I need to have a good video for them as well. Thank you. All right, so we just made real particles. Are you real particles? Yeah. So is this how you were born? Yeah, this is us. This is how we came into existence. And there's also neutrinos, those ghost particles. That's also our grandpa, real grandpa. But the original grandpa is space, right? Once the space is born, then we're born with the space. So that's how matter was born. Lots and lots of matter, because there's lots and lots of energy, tremendous amounts of energy, all the energy in the universe, in the size of a pea. Imagine that. Well, that pea is a billion times smaller than an atom, so tiny pea. But it's got those little things on it, little, what do you call it, little, holes in it like that. That's because of the atoms not being there. Sometimes they're there, sometimes they're not there. That's why we gave them dimples to the pea. All right. So now here's another way you can make these particles real. This is singularity, black hole. This is the event horizon. Inside, infinite curvature of space and time. Outside, not infinite curvature of outside. So this is not infinite curvature, infinite curvature. Well, what if happens if there's a particle and an antiparticle here? Well, if there's a particle and antiparticle right at the edge of the event horizon, either the particle or antiparticle can be released into space. The other one will go in. So antiparticle or particle will go into the singularity, and the other guy is released to space. This is called Hawking radiation. So Stephen Hawking said that black holes are not black. They're actually emitting particles. They're emitting particles or antiparticles all the time, because they're making virtual particles of space. That's what space is, into real particles. Antiparticle is a real particle. Now the question is, where are the particles and antiparticles? So particles is us. Like, I am particle. Where is antiparticle? We don't know. That's a huge question. The answer from Stephen Hawking was, well, okay. So let's say we had a billion particles and 999,999,999 antiparticles. So 1 in a billion more particles. So those particles will have taken over eventually. Given billions of years, particles will dominate. Somehow the particles have dominated. I mean, you guys haven't seen any antiparticles lately, have you? Because if you do, let me know. If we have like antiparticle, even a small, tiny antiparticle will destroy San Diego. You know, it's like the most dangerous bomb there is. So that's how you make matter. This one here is called particle pair production. That's how you produce a particle pair. The other one only makes one or the other, either positron or an electron, not both, because one of them has to fall into the singularity, right? Okay, like if it wasn't difficult enough, we have to introduce something else. Something else is going to give you guys a different view of space from now on. Space is everything, you guys. Space is everything. So what do I say? Space is everything. Well, this is today. Let me show you just what's going on today. Everything that we've talked about so far, gases, black holes, you, me, life everywhere, planets, suns, galaxies, everything that we talked about makes up 4.6% of the mass of the entire universe. So this is the entire universe here, mass of the entire universe. Dark matter, which we don't know what the heck it is, but it's got about 5 times more mass than regular matter. So there's some unknown particle. We haven't found it. That's why we call it dark matter. It's about 23% of the mass of the entire universe. So what's the other 70-some% of the entire mass of the universe? Space. This is space. Space has got something called dark energy. Dark energy is in space. It's an energy inside of space. Like if you have some space, you have dark energy. Sheesh. So this dark energy is what's making the universe expand. If I had a cup of dark energy in space, I could make myself a new universe. Just, I need time. So if I had dark energy, I could make a new universe like that. No worries. So in space, there is an energy. It's an unknown form of energy. That's why we call it dark energy. It's very tiny. Imagine the amount of dark energy is like 100 two zeros, then a 1. Ha! That's really, really tiny. But then look how much space there is. There's so much space. So because of that, dark energy makes up equivalent mass of 72% of the entire universe. So this is when the universe was born. As you notice, there is no dark energy. There's dark matter. Dark matter is taken over here. And most likely we have a lot of black holes because there's so much dark matter. Now, there's a question here. All the stuff that we see, we call, black holes, there could as well be very, very dense dark matter. There's nothing that says it can be dark matter. Like we have a supermassive black hole in the center of our galaxy. That could just be a very, very dense spot that is just dark matter. Possible. Because dark matter is surrounding us. So anyways, so there's a lot of dark matter, a lot less dark matter, a lot more dark energy now. So lots and lots of neutrinos. 10% of the original stuff was neutrinos, lots and lots of photons. Now atoms make about 12%. I showed you how you make atoms. So those atoms are only 12%. And protons and electrons and neutrons, they're not together yet. You haven't made any real atoms yet at the beginning. It's going to take a while. These two guys, my friends, Penzias and Wilson, right? Wilson and Penzias. So Wilson and Penzias were given an assignment by Ma Bell. Ma Bell is like grandpa of AT&T. All right, these guys engineers. So these two engineers were trying to fix the telephone lines. You guys are all young, so you don't remember. But in the 40s and 50s, I don't remember either, but I've been told. Telephone lines are very noisy. So if you talk to your grandma in New York City, all you hear was, "Hi, grandma," it's like that. So these guys were in charge of cleaning up the telephone lines. Like, what's the problem with the telephone lines? So they got this horn antenna. It looks like a giant horn. It's a microwave antenna. They're trying to pick up microwaves. So they got some noise from everywhere. They looked at up, down, left, right, everywhere. Uniform noise everywhere, coming from everywhere in the universe. The earth, they up, everywhere, just, And this microwave ended up being like equivalent to 3 degrees Kelvin, right? Really cold, right? Well, it turned out what they were looking at was the remnant of the Big Bang. This is the first time we can actually see now the remnant of Big Bang. So, like, if I went camping with you guys, we made a big giant fire. That giant fire will be the Big Bang. Then we go to sleep, wake up the next day, we look at the fire, all we see is embers. So these guys find the embers of the Big Bang. What does the ember of the Big Bang look like? Well, the ember of the Big Bang looks like this. This is the ember of the Big Bang. What the heck is this? This is the entire universe. So this is a map of the whole universe. In fact, Milky Way would be here in the center at the equator of this universe. This would be like a northern sky, southern sky, like that. Not exactly, close enough. I believe this is galactic coordinates. So it's like this is the northern part of the galaxy will be here, southern part of the galaxy will be here. We remove the galaxy's picture here because the galaxy always gives us some microwaves as well. So this is a microwave map of the whole sky. And this is the best technology we've ever had. So we know microwave is coming from 1940s and 50s, the experiments. But what we didn't know was there was temperature differences in microwave. Temperature differences in the microwave background, we call it, are approximately 1 part in 10,000th of a degree. So like 1 part is 10,000 degrees, the other part is 10,000.1 degree, right? Like that, right? I'm sorry, 10,000.0001 degree, like that, tiny. So the red is the hottest part, the black is the coolest part. So we can see hot stuff, a little cooler, yellow, a little cooler, green cooler, blue cooler, dark blue cooler, black cooler. So what this translates to later on, what do you think it is? This is a blueprint of the future universe. And sort of like you can see Friends on TV 17 years ago when it ended, the last episode of Friends is now visible on a planet that is 17 light years away from the Earth. So those guys just got the last episode of Friends. So in the same way, we're looking at the Big Bang. This is 375,000 years into the age of the Big Bang, age of the universe. So when the universe was this young, that's what the universe looks like. Now, with normal Big Bang, you don't get this. You don't get this because the temperature should not be within 1/10,000th of a degree everywhere. There should be a lot more differences because what sends the temperature from one side of the universe to the other side of the universe? Light. Well, light wouldn't have time to go all the way here. But inflation allows you to get this gigantic thing in a fraction of a second. That's why the temperatures are so close together, right? That's why. So the red stuff and the dark stuff, what's going to happen to them? Aha! So what's going to happen is future galaxies are going to be the red stuff. So those red patches are going to become the cluster of galaxies. So when you see a cluster of galaxies in a filament that I showed you on Tuesday, their blueprint is right here. Those red dots that I showed you, they're going to become it. Well, what about those dark spots? They're going to become the voids. That's where there's voids. There's nothing. Well, very, very few galaxies anyways. There's voids. Remember, when you look at the filaments, there's voids, and then there's filaments. So these are the voids. The voids are these dark spots here. The filaments are just all these red patches here. All right? So this explains to us what the universe is all about, basically. So now that you know everything, let's talk about the history of the entire universe. So there you have it, the history of the entire universe. So this is P instanton. This is when the whole universe is going to begin with those quantum fluctuations. In other words, remember how that electron went over the hill and it just appeared? Well, if I had an electron, that electron will open up the floodgates for me. I can start another universe. Do I need to? No, I don't need to start another universe. We already have enough trouble. So universe starts here, times 0. This is the inflation period. Very quickly, universe became gigantic, right? And then we can see the afterglow about 375,000 years after the Big Bang. Then there was a period called Dark Ages. So what's that about? Well, between the afterglow, where we can see the 3-degree Kelvin background radiation, and it doesn't matter, by the way, which direction you look, you see this. In fact, you can see this with your TV set. If your TV set is showing you snow, you know, those little snow things, like 10% of that is the Big Bang. You're looking at the Big Bang, amazingly. The old TV sets that were not digital, they're even better. They can pick up the snow really well. Like 90% of that picture that you see as snow, that's the Big Bang. You're looking at that afterglow of the Big Bang. So the background radiation, 375,000 years. Now you got to finish building stars and galaxies. So there's a period of time when there is not enough light. We call it dark ages because the stars are not born yet. First stars are born somewhere between 100 million years and 200 million years after the Big Bang. So that's why we need that new space telescope, the Webb Space Telescope. That Webb Space Telescope will allow us to see all of these guys, the very first galaxies and stars. Before that, dark ages, you can't see anything. Before that, you can see the afterglow. Someday we'll be able to see, I bet you, we can get to see maybe God in his kitchen building the universe. You know, he's probably doing something here. We don't know. But regardless, if there is a God, he's timeless, he's spaceless. He doesn't need time, he doesn't need space. That's God. So don't imagine him as some, you know, guy or girl with long hair or something in the sky. It's just silly. All right, now, after the very first stars are born, the universe is expanding because of dark energy. So dark energy and the Big Bang gives it the initial push. Dark energy takes it the rest of the way. For about 5 billion years after the Big Bang, space grows and grows. And by the way, each one of these lines represents 1 billion years, like 1 billion years, 2 billion years, 3 billion years, 4 billion years. The age is about 13.8 billion years. You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 0.8 is over here. So for about, approximately 5 billion years, the universe was okay. Everything was just coasting. And then at that point, there was a lot of mass. There was a lot of galaxies. There was a lot of everything, gas. That was holding back dark energy from making the universe expand. And then dark energy becomes king. Dark energy is making the universe expand faster and faster and faster, meaning that at the end, we're going to end up with this gigantic universe the galaxies would have died, the stars would have died, everything would have died except for space. It'll keep going forever and ever, right? So that baby will keep on going, but there'll be only light. And like I told you before, light is timeless. So if you come back to that period of time, it'd be just like the Big Bang. It's timeless. You go, what time is it? Well, you ask a photon, what time is it? Photon will say, I don't know. There's no time. What is time? So Roger Penrose, who's the only one left over from the original Big Bang guys, British guy, he's got a theory that the Big Bang is just that period. It's a period where universe had ended, another universe had ended, and another one begins because there is no time then either. At the very end, it'd be just like there's no time. I mean, who's keeping time? If there's just space and photons, nobody can keep time then. That's a kind of a weird theory, but regardless. By the way, this is WMAP. This is the guy that did the picture of the background radiation. And it's like fantastic technology, just amazingly fantastic technology. Now, we can go, I guess, so this is dark energy accelerates expansion. So is it going to go faster than the speed of light? Yes, it's going to go much, much faster than the speed of light. Universe will become humongous, and there's no end to it, how big it's going to get. It's just going to get huge. Even the, white dwarfs are going to cool down and die. Everything's going to die. There's no matter. There's no hydrogen atoms have decayed. Everything is decayed. No matter is left. Nothing. No. This is what we got right now, though, right? These are the filaments of galaxies and everything in the universe. And we happen to be right here when we make the map, of course, because we're the center of the universe, since it doesn't matter which direction you look. Remember, universe is isotropic, is homogeneous and all that. So we're here, we're in the center of the universe. Everything is moving away from us. And if you were here, this would be the center of your universe. So you'd be here if you were here. Regardless, the universe is approximately 93 billion light years across. That's the diameter of the universe. I think the age is more important because we know the age fairly close. It's about 13.77 billion years since the Big Bang. You can remember it as 13.8 billion years since the Big Bang. And this is the Virgo supercluster. From here, when we look around, we can see about 46.5 billion light years around us. Doesn't matter which direction we look, we can see. So that's the observable universe, right?
What is the age exactly again?
13.77 billion years.
And that is 28 billion parsecs?
I'm sorry?
On the chart, it says 28 billion parsecs. So does that...
93 billion light years is equal to 28 billion parsecs. One parsec, remember, is 3.26 light years. So if you multiply 28 times 3.26, you get 93 billion.
Thank you.
You're welcome. So pretty soon there'll be galaxies that we can't see anymore. They'll go over our horizon. They'll be over here. And they'll be moving much, much faster than the speed of light. So if they're going faster than the speed of light, you're out of luck. You'll never be able to see it. Right? So this is what we can see. So there's a lot of stuff here. We just can't see it. We'll never be able to see it. All right, so depending on what kind of a curve the universe has, if you have a lot of mass, we have a closed universe, all right, which means the universe is going to collapse, like the Indian mythology, right? The universe is going to expand and then collapse, creation and destruction, right? Like that. Doesn't seem to be the case here. Then we have a flat universe. So the question is right now between flat universe and an open universe. So in a flat universe, we're going to be kind of coasting forever and ever. In an open universe, we're going to be accelerating. The universe is going to get bigger and bigger and bigger. This is called a saddle, like a horse has a saddle. This is like a saddle, like a negative curvature. We think this is either this or this. I like this myself, but I don't know. I'm not a cosmologist. But I have something interesting to tell you. It turns out that inflation hasn't ended in all parts of the universe yet. There are some parts of the universe where inflation still exists. Like there's a huge amount of energy some places, like here, 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 like that. Like some part of the universe, there's still energy. Sheesh. What's going to happen now? Well, that is going to make another universe. So, am I saying that maybe the universe is giving birth to other universes? That's exactly what I'm telling you, that our universe may be giving birth to other universes because inflation is eternal. Eternal inflation means forever. So, we're giving more and more births to more and more universes. In fact, if this is the case, there should be like infinite number of universes. We just be one of many, 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 many universes like this,
I have
right?
a question.
Yes, please.
If parts of our universe are constantly inflating, is it expanding upon our universe, or like where is the other universe?
No, no, I'll show you in just a second. I'll show you just a second. So we're just giving birth, like we're giving birth to 3 universes right now. Those 3 giving birth to another 3. You can see how many universes can be, made. Each one will have a different rate of expansion. So dark energy is going to be a little different here, here, here. Dark energy in our universe is extremely tiny, or there'd be no planets, there'd be no suns, nothing, right? So these universes are probably very strange and varied. We probably don't even know what kind of a life exists out there in these universes. So question should be answered, right? You just asked me, where are the other universes? The other universes are being born, but like our universe, those universes are expanding faster than the speed of light. The right question to ask is, where are those universes expanding into? And the answer is hyperspace, which means higher dimensional space, which means 4th dimension. So surface is surrounded by 3 dimensions, right? If you have a sheet of paper, it's surrounded by volume of space. So a sheet of space is surrounded by space, right? There's space, all around it. So what is, all around space, all around our universe? Higher dimensional space. Like this is higher dimensional space surrounding a flat space. So in the same sense, we're floating in higher dimensional space. So now the last thing I want to tell you is this. It's kind of funny actually. If this is true and we have all these infinite number of universes, then the possibility that there is another Kelsey someplace in the universe is pretty darn good. But now she's not in astronomy class. She could be like in a geometry class with like a blue dress on, and she's maybe colored her hair green. Who knows, right? Or maybe there's another Linda who happens to be a conductor of music. Who knows, right?